Hi there. Thanks for joining us on the Q&A edition of Space Nuts. My name is Andrew Dunkley, your host. On this episode, we're going to be answering questions about light. It's an interesting question about how far away light has to travel before it's undetectable, and he even gives you a measurement of how strong that light is. So we'll talk about that. Are we living in a holographic universe? I think we've had that question in several forms over several years, so we will tackle that one again. And how fast is fast enough to create drag when traveling through space? And what's the trouble with this word? Relativistic speed. That's all coming up on this edition of Space Nuts Q&A.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again for more. Don't ask me why. Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. It's good to be back.
It is.
Whatever the reason is.
Yes, indeed. Everything good?
Yeah, all good. We're all firing on 2 cylinders as usual, so that's
yes. Yes. Yeah. The trouble is we're driving a V8. Anyway.
Yes. That's right. That's right. Yeah.
Shall we get on with it and go straight to our first question? This one comes from Alan.
Hi, this is Alan Scahill from Medicine Hat, Canada. My question is, if an LED light, 1 candle power in strength, were to be turned on in space, what would be the greatest distance a space telescope would be able to detect it? Thank you and love your podcast.
Thank you, Alan. Medicine Hat. Did you say Medicine Hat in Canada?
Yep.
That's an interesting name. I wonder why it's called that.
He might have to tell us. We might want to know why he's got a British accent as well.
That happens. Yes. I could ask the same about you.
That's a really good point. I'd never thought of that.
Yes. Medicine Hat is a city in southeast Alberta. It's located along the South Saskatchewan River. It's approximately 169 kilometres east of Lethbridge, 295 kilometres southeast of Calgary. The city and the adjacent town of Redcliffe to the northwest are within Cypress County. So there it is. Doesn't say why it's called Medicine Hat, though.
It's a great name.
It might have something to do with a nearby mountain, I suspect.
Yeah. It's the nearest we got to it during our expedition last month was to Calgary. We flew out of Calgary when we left.
Isn't Calgary a lovely place?
The bits I saw of it looked very nice. Yes, that's right. But it was only the airport, really. We were travelling down from Lake Louise that day, and Lake Louise is stunning. So I can answer for that. I think you've been...
I was wrong. It's got nothing to do with a mountain. Apparently, it's derived from the Blackfoot Indian word samus, meaning the headdress of the medicine man.
There you go. There you go.
If I'm looking at the right place, I just did that quickly. I stand to be corrected, Alan, so please, if I'm wrong, let me know. LED light.
Yeah, 1 candle power.
1 candle power. How far out before we can't see it, or something to that effect?
I've no idea. Look, it's all about. And this is the interesting thing about light. It's yes, we regard it as a stream of photons, but it's also a wave motion, and light is something that basically has infinite travel possibility. And so that one, the photons that 1 candle power is emitting, or the light waves that the LED is emitting, essentially go on forever. But what limits your ability to detect them is the equipment that you've got to do that. And if you've got, and that's the key thing about telescopes. The bigger your telescope, the bigger the light gathering area of your telescope, the fainter the objects you can see, and therefore the further away you'll be able to see your 1 candle power LED. I might take it on notice, Andrew, and see if I can do a calculation for that, because I do this sort of thing, or I used to when I was thinking about star magnitudes and things like that. So it's a 1 candle power LED, and how far away could, for example, the Hubble Space Telescope see?
I did have a quick look myself, and I just found this on the physicsforums.com website, and it says, and you said this earlier, there is no known limit to how far light can travel.
Yes, that's right.
But we're talking about the detectability of it.
Indeed, and that it depends on the instrument. And I think Alan mentioned the Hubble, or just a space telescope. Anyway, it doesn't matter. We'll try and do some calculations on that.
Okay. Well, that was easy.
No, it wasn't. Well, it was easy in the sense that, the answer is that light goes on forever, basically. It's just whether you can detect it or not that's the tricky bit.
That's the hard part, yeah, for sure. Okay, Alan, we'll get back to you shortly. Now, let's move on to our next question. This is a text question that came in from Charles. What do you think of the theory that we live in a holographic universe? Now, we better qualify that by explaining what a holographic universe actually is, or is supposed to be. Let's just say that.
So let's quote Leonard Susskind, who was one of the great proponents of the holographic universe. The quote is, the three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders and people, is a hologram, an image of reality coded on a distant two-dimensional surface. There you go. When does that date from, that quote? It's probably about 25 years ago, because that's how long this thinking has been going on about the holography. Actually, that goes back only to 2008. And it's from his book, The Black Hole War, My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics. I love the title. I haven't read that. So what you've got is the idea, and it comes from, so think about what a hologram is. It is a way of encoding light. It's actually, we would call it an interferogram in the world of physics. You've got a film, in fact, a two-dimensional surface, which is transparent, that has a pattern on it, which, when you illuminate it with what we call coherent light, that's light from a laser, where all the waves are in step, all the light waves are in step with each other, then it will, basically that light will be diffracted, it will break up to form a three-dimensional image. One of the best holograms I know of is at Macquarie University in the physics department. I have an honorary appointment there, so I go there quite a lot. And what they've got is it's actually it's a conference room, just a small conference room with a table and chairs in it. But one wall of it is lined with windows, and on the other side of the windows is a corridor where you can walk. And that window, the windows have a hologram on them. And so when you look through the hologram, through the window, at what is in fact just a room full of chairs, what you see is a succession of images of a bar as the night wears on. And the bottles are full to start with, and everything's neat and tidy. By the time you get to the other end of it, there's empty bottles all over the place. It's really not in good shape. So that is what we normally think of as a hologram. It's something that gives us a three-dimensional representation of from a two-dimensional source. So this idea that the universe is like that, I've always had trouble with, because a direct analog with a hologram is that you illuminate it with something, and the illumination forms that three-dimensional image. And so where does the illumination come from in the holographic universe? So I think you've really got to look at the details of this. And, if I can read from the Wikipedia entry on holographic principle, which is what it's all about, the holographic principle is a property of string theories and a supposed property of quantum gravity that states that the description of a volume of space can be thought of as encoded on a lower dimensional boundary to the region, such as a light-like boundary, like a gravitational horizon. There you go. So that's what you're supposed to imagine with a holographic universe. So it's
Right.
as I said, it goes back 25 years, probably more than that. I've never been that keen on it because it seems highly contrived to me, but it does have a theoretical basis for people to think it might be the case. I'd like to see more evidence that there is a holographic event horizon, if I can put it that way, because I think that's the idea that if we're a black hole, the event horizon is actually where the hologram lies. And there's a whole lot of gobbledygook on the Wikipedia page that if Charles wants to plough through, he might be even more illuminated on it than I am. Less.
I find the theory very confusing. It doesn't sort of glean with traditional thinking. And
it's not intuitive. That's right.
I find it hard to argue against traditional thinking.
Yes, I understand that. I think by traditional thinking, I think you might mean something that makes sense.
Yes. The way we generally understand things at the moment is traditional thinking. That's my perception of it.
Depends who you are, really, doesn't it?
I
do
guess.
the thinking.
Yeah. Well, that's it. I mean, we should be open to all possibilities because the mystery of our existence at all is one we can't answer.
Yeah,
we don't know why it happened. We don't know what caused it to happen. We don't know how things developed to create what has been created. The more we look, the more questions that are raised, the more we get confused about things that shouldn't have been able to happen that happened. I mean, it just goes on and on and on. So you can't write off anything, I suppose.
No, and I wouldn't write off the holographic principle either. I think it's a really interesting idea. I don't fully understand it, as you probably realise by now.
I don't understand it that much.
And that's so we. So the answer to Charles's question is, yeah, I think it's interesting. As I said, I've never been a big fan. That's because I perhaps am a traditional thinker, as you would put it, and like to think about the universe as being made of atoms and things that really owe their existence not to a hologram, but to being where we are, to being within a universe that was created in a Big Bang and has all these other particles generated from that in it. That makes more sense to me.
The next question that's going to come up is, hang on a minute, what if the hologram is made of dark matter?
Ah, yes. I think you've put your finger on something there.
Oh, you reckon? Probably just stirred the pot even more and made it murkier. Yeah. But the holographic universe theory is fantastic in science fiction. It really is.
Yes. Yeah.
I am actually watching a TV series at the moment, which I'm thoroughly enjoying. It's called Dark Matter. And it centers around multiple universe theory.
Mm-hmm.
And I was going to take a little bit of a break, but we might as well throw straight into this. This is about a bloke who gets abducted, and when he wakes up, he's in a different universe. And he's trying to figure out what the hell happened because it's the world, but not as he knows it. Same people, different situations, different relationships, different career path situations. It's all out of whack, and he thinks he's going mad. There's only been 3 episodes so far, but gee, it's good. It is really good. But the reason I bring it up, and thanks for your question, Charles, but this question popped into mind, and I'm giving it to you without notice, from Rennie, who is a regular contributor. Could it be possible that our universe is in a universe cluster as our Milky Way is in a galaxy cluster? If all universes are expanding, would they eventually overlap each other at some point?
I think the sort of standard multiverse idea is exactly that you've got multiple universes which may be clustered together or not necessarily. One way of looking at this is the M theory universe, and M, nobody's ever sure what M stands for. Mystery, membrane is probably where it comes from, because the idea is that we are all on a living in a 3-dimensional membrane, which is right next to other 3-dimensional membranes that contain other universes. And when membranes collide, you get a Big Bang.
Yeah.
That theory, I I remember checking it out once in quite some detail, and we think of these membranes as being membranes with a universe somehow imprinted on it, but it turned out in the theory, it's actually, when I think about it, it's called the ekpyrotic theory of the origin of the universe, and it turns out that these membranes are only separated by something like 0.5 of a millimeter. And when they collide, you get a big bang, and you're thinking, oh, that's a bit close. Something went wrong. I'm not sure where M theory is at the moment in terms of its acceptance by the cosmological community. But I think the answer to Rennie's question is yes, that's possible.
And if they keep expanding, which ours is, would they eventually overlap at some point? I'm not sure overlap would be. I mean, what if two universes that are expanding bump into each other? I think bump would be an understatement.
Yeah, but they might be expanding in a higher dimensional space, which might preclude that.
Well, there's a thought too. And here's another thought. If you've got two universes expanding towards each other, and let's just say ours is one of them, ours is expanding at an accelerating rate. What if the one that's nearest is expanding at an accelerating rate, but their acceleration's faster than ours? Now, it doesn't stand to reason that we're all going to hit at exactly the same speed.
No, I think you've got to ensure that your other universe is in a different bit of the higher dimensional space than you are, and then it can expand as much as it likes, and it doesn't hit ours unless it's a membrane. And then if it's a membrane and it collides with ours, you get a big bang. Yeah,
it's just like watching child's balloons burst or bubbles bumping into each other.
That's right.
They go boom. Yes, they could be mini universes that live for a fleeting moment, and the people go, "Oh, look at done."
No, it's gone.
It's really interesting to talk about that. It's a fascinating theory, and this dark matter series sort of leans on that particular multiverse theory very, very well. And they travel around in a box, just like Doctor Who did.
Really?
Yeah.
Okay.
Thanks, Rennie. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all four systems and keying with a go.
Space Nuts.
One more question, Fred, and this one comes from Craig.
Professors, I'm Craig Miller, calling from sunny Merimbula in New South Wales. I have a confession. I have a solitary habit I don't usually mention in public. I write science fiction.
Oh.
Thus, this question is a little what if. The vacuum of space is, as we know, not exactly empty. The density is low, but gas and dust fill the vacuum of space. So I'm wondering how fast you would have to be travelling before that gas and dust began to produce drag. Surely if you went fast enough, you'd have to consider aerodynamic principles for the profile of your spaceship. As a secondary question, wouldn't a ship travelling at relativistic speed smash into that aforementioned gas and dust like a mobile particle collider? If there were lots of spaceships travelling at light speed, you'd see the trails all over the sky. Maybe. Anyway, thanks for answering my question. Keep up with the great work. I love your show. Thanks very much. Ciao.
Thank you very much, Craig. Lovely to hear from you. You'll have to send us some book titles. I'd like to take a look at those, if you don't mind. I'd love to see what your angle is in science fiction and steal your ideas. No, I'm kidding. Now, my thoughts on his first question, how much speed to create the drag in the vacuum of space would be dependent on the concentration of particles, would it not? Because some parts of space only have one speck of stuff per gazillion miles. No, I'm exaggerating slightly.
Well, you're not exaggerating that much. Maybe the gazillion is a bit. It's some yes, you're at the level of a handful of particles per cubic meter. And it's a really interesting question, actually, that Craig that he poses, because even at those low densities, so we've got a sort of a bit of an example of this around the Earth. When you get to heights of 100, 200, 300 kilometers, there's still enough of the atmosphere that you're going to get drag on your spacecraft if it's in orbit, and that's what brings them down. So here's the International Space Station, 400 kilometers high. That has to have its orbit boosted periodically, every few months, I think, in order to counteract the effects of drag. And there's not that many atoms of atmosphere up at that height. It's certainly well over 1 per cubic meter. But yes, so the atmospheric drag on a spacecraft is a real thing. And I think to extrapolate that, as Craig is doing, is actually a valid thing to do. Should you think in aerodynamic terms if you were designing very, very high-speed spacecraft? And I think the answer is probably in the second part of Craig's question, because yes, at those relativistic velocities where you are approaching the speed of light, then your spacecraft is more like a particle accelerator. It's more like what's going on at the Large Hadron Collider, where you might well see, atomic scale impacts that would have showers of other particles coming off them. So your occupants of your spacecraft might be being irradiated by highly ionizing radiation from the particle impacts that you're traveling through, which would be not very nice. If you've got dangerous rays coming out the walls of your spacecraft, no matter how aerodynamic it is, you're not going to be very happy about it. No. So I don't know the specific answers to the questions, but it's a really interesting one. I can't tell you what velocity you really need to think about designing. And you're absolutely right as well, Andrew, in that different bits of space have got different densities. If you're looking at a star formation region, a nebula, as we would see it as, the pressure there is unbelievably low. It's lower than the hardest vacuum you can make on the Earth. But there are still enough particles there that you're essentially forming a nebula. You're seeing the glow of it. Whereas in regions between the galaxies, the density of particles is very low indeed. But it's still there. They're still there. The particles, subatomic particles, are still there. So yeah,
if you were capable of traveling at near light speed and you wanted to travel any significant distance, you'd have to really be able to calculate your navigation with so many parameters in play. It's not just about, I want to go from there to there, because there won't be there when you get there. It'll be there somewhere, and you've got to allow for what's in between to make the trip without sort of hitting something, like a giant star or whatever. I think interstellar navigation would be a very tricky little thing to deal with.
Tricky job. Well, we've got spacecraft that are doing that. Basically with the Voyagers and the Pioneers, they're in effectively interstellar space. They're still feeling, not all of them, but some of them are feeling the magnetic field of the sun rather than the magnetic field of the galaxy. I think Voyager 1 feels the magnetic field of the galaxy. You're out there in very deep space. I wonder whether, we certainly, I'm just trying to think of this the other way around. Particles, what they do, when I was building instruments for ground-based astronomy back in the 80s, 90s, early 2000s, we were often beset by the effect of cosmic rays, which are subatomic particles coming in at very high speed, on our detectors. You'd get you get an image that was supposed to be the spectrum of an object, but it have all these. It looks as though somebody had thrown a whole lot of just white bits of sand all over the image, and they were the impacts of cosmic rays which were being recorded by the detector.
Wow!
So that sort of thing must happen when you've got a spacecraft, that's doing science or imaging or whatever. You must have this cosmic ray flux anyway, But if you've got a significant velocity in a particular direction, that might affect the cosmic ray flux. You might see more than you expected, or less than you expected. Yeah, it's a really interesting thought, and thank you for bending our minds in that direction, Craig. It's
indeed
fun to have. Yeah.
Yes, and I mean it when I say send me some info about your sci-fi books. I'd love to see what you write about. And if you do have questions for us, of course, please send them through our website, spacenutspodcast.com or spacenuts.io. You can click on the AMA link at the top and send us text and audio questions, or the little purple button on the right-hand side to send audio questions only. But as we always say, please remember to tell us who you are and where you're from. You might be from Medicine Hat in Canada. Who knows? And thanks to everyone who contributed, Alan, Charles, Rennie and Craig. Looking forward to some new questions in coming weeks. And that wraps it up for another episode. Fred, thank you very much.
Oh, thank you. Thanks for having me. And thanks for everybody's questions. It's very stimulating.
It is, isn't it? Gets your brain going sometimes.
Yeah, it certainly does, yeah.
People do tend to think outside the box a lot. Yeah. Thanks, Fred. We'll see you soon.
See you later. Cheers for now. Bye-bye.
Bye. Fred Watson, astronomer at large, and Hugh in the studio, who does what Hugh does in the studio when he's not in the studio. I don't know what he does. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts, coming to you real soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.